Hello, I am Christian Malaga, and in this video I will discuss some basic principles of computer vision sensing. The focus of this short video is on displacement measurement using computer vision in the context of structural dynamics. A computer vision sensor system typically consists of a digital video camera, a zoom lens, and a computing unit. The digital video camera will turn light into discrete signals. The resolution of a digital camera refers to the pixel count contained in an image, usually given in columns by rows. The frame rate is the number of images or frames captured in a given time period and is usually expressed in frames per second. This slide presents all low-cost off-the-shelf components, including a Raspberry Pi and a Pi camera. Here we can see a depiction of the concept of using computer vision for measuring structural displacements. First, the camera is fixed in a given point and takes a video of the structure or the part of the structure of interest. The computing unit acquires and processes the video images to extract displacements either in real time or after post-processing. It is worth noting that the images can always be post-processed to alter the measurement point, a useful feature that is not available in other structural sensing systems. When conducting multi-point measurement of large structures, multiple synchronized cameras can be used, each one pointing to different parts of the structure to get a whole image of the structural response. Computer vision displacement sensing largely uses template matching to track objects. Template matching is one of the most effective image processing techniques, and it has been implemented in a good number of freely available algorithms. First, an initial area of the image is defined as the template in the first image of the video sequence. This template is located in subsequent images of the series by means of a template matching technique. Template matching is computationally expensive, and in order to reduce the computational time, the search area is usually restricted to a predefined ROI, or region of interest. The displacement of the template is measured based on the pixel coordinates and converted into a physical displacement by means of a scaling factor. Template-based techniques can be generally classified as area-based or feature-based. Area-based template matching techniques are also known as correlation-like methods. To identify the matching area, the template image is compared against the source image by moving it one pixel at a time. At each location, a metric is calculated to represent the similarity between the template image and the particular area of the source image. One of such metrics is the normalized cross-correlation. The peak of the cross-correlation matrix occurs where the template and the source image are best correlated, enabling the location of the template coordinates in successive source images. One of those template matching techniques was proposed by Guisard and Sicairos in 2008 to achieve sub-pixel resolution. Consider a pair of images F and T with identical dimensions m by n. Image T has a relative translation from the reference image F. The cross-correlation between images F and T can be defined using the Fourier transform. As we have seen in a previous video, the Fourier transform allows us to get an appreciation of the frequency content of a series. In this case, we are working with coordinates, and the Fourier transform will return the spatial distribution of the frequency components of an image. The initial displacement can be estimated from the peak of the correlation between successive images. Subsequently, a second search is conducted to achieve a sub-pixel resolution. First, the cross-correlation is computed in a 1.5 by 1.5 pixel neighborhood around the initial estimate by an upsampling factor of k. Hence, a sub-pixel resolution within 1/k of a pixel is achieved. For example, by setting k equal to 10, a 0.1 subpixel accuracy can be achieved. This is usually not done by zero padding, but instead by matrix manipulation. This is because zero padding can lead to substantial computational costs. Once the new peak is identified with coordinates x local and y local, the final subpixel resolution coordinates can be computed. To measure the displacement of an object from captured video images, the relationship between the image coordinates in pixels or pixel fractions and physical coordinates in millimeters or centimeters must be determined. Based on this, a scaling factor or a conversion ratio will be established. This scaling factor can be determined based on 1. The intrinsic parameters of the camera, as well as the extrinsic parameters between the camera and the object, which is known as camera calibration methods. Or 2. By relationships between the known physical dimensions of the object and the corresponding image dimensions in pixels, commonly referred to as practical calibration method. Camera calibration methods use special calibration patterns to estimate the parameters necessary to determine the scaling factors to be used on the images. After obtaining the camera parameters, the world coordinates of any image point can be reconstructed from its image coordinates. The most frequently adopted pinhole model for camera calibration relates the 3D world coordinates x, y, and z of a calibration target point with its corresponding location u and v in the image plan using the perspective projection equation presented here. In this equation, S is the scaling factor, Fx and Fy are the horizontal and vertical focal lengths expressed in pixels, Cx and Cy are the coordinates of a principal point, usually at the center, and gamma is a skew factor. The extrinsic parameters r and t represent a rigid rotation and translation transformation from the 3D world coordinate to the camera coordinate system. Camera calibration can be performed using the OpenCV calibration packages in MATLAB. To calibrate the camera, multiple images of a calibration pattern are needed from different angles. Various checkboard patterns can be used for this purpose. One of the main limitations of camera calibration methods is that they require one-time access to the target object to install the calibration panel. This access can be difficult in the field. To overcome this limitation, more practical calibration methods have been developed. This figure shows a practical determination of the scaling factor when the optical axis is non-perpendicular to the object surface. In this case, we are assuming that we know the real-world physical distance between A and B beforehand. With this value, and assuming the camera optical axis is tilted from the normal directions of the object surface by an angle theta, we can apply geometric relationships and estimate the scaling factor with this expression. Hence, the scaling factor can be estimated as XA minus XB over IA minus IB, where XA and XB are the coordinates of the 2 points in the line AB, and IA and IB are the corresponding pixel coordinates in the image plane. From geometry, XA and XB can be estimated by means of these expressions. Moreover, if the angle theta is small, the expressions for the scaling factor can be simplified as shown here, where capital D is the distance between the camera and the object, the pixel is the pixel size, and f is the camera focal length. In this course, we will be using a scaling factor calculated based on a known physical dimension on the experimental object and its corresponding image dimensions in pixels. All the principles and procedures presented here will be applied to the structural displacement measurement in our dynamics coursework.